Yeah, good morning. Welcome back to the first day of the week. We are going to have a weekend. Yeah. Um, here we would like to remind you that our first home is at Hill, grade 11. Not very tough one. But for you in this chapter we remember some definition object in your image because easier. Let me find a quiz. Okay, midterm. Okay, yeah, you have to know what's the pixel defined by A adjacency, O adjacency, M adjacency. Okay, remember that. So this video I think is to cover everything here. Or what we have defined in last lecture, and this is A is like the arrangement of pixel, and you can see this dotted line. A adjacent right here. This dotted line here. I can ask you. Never they are adjacent. Never element. So domain here. Because you are going to write the program yourself. You are going to hand out A4. Okay. So the C one, even you can extend it your relationship of this adjacency any subject area. For example, like this one, R and J, this is the question 4. This is the D. D is a two region, and these two regions, R1, Ri, and Rj are 8. Listen, why? Because the pixel in the Ri subject component and Rj subject component have this one value. They are 8 adjacent. So these subjects are also 8 adjacent for these two regions, sub-regions. I can change. Are they n adjacent for these two subjects? N adjacent. Yes or no? Remember the n adjacent definition. There should be two different criteria, right? One is there are four adjacent, or their intersection pixel empty or not. So they are empty. So fine. Regions are n adjacent. Okay. So please go back and read the definition of this. 3 different adjacency definition. And for this E, the circle point only if edge is between the region and background. So we are asking if this pixel is the boundary point or not. Therefore, this subject, this pixel is located on the boundary of the one value connect component. This is the boundary. Under which definition you have to announce first. So there's some different definitions. There might be different results. Okay, so here the question is asking, this is the adjacency of this subject. It is the boundary point. Okay, so they told you the circle located in this boundary of this circle one value document only if adjacency between the region and background is used. Only it is adjacency. This is the boundary point. How about 4? This is the boundary point for the 4 adjacency under 4. Yes or no? Answer is no. Because this this is not boundary point for adjacency. For this boundary background, this is object. For adjacency boundary, only these 2 points will be defined as a boundary point, but this one is not. No point. This subject. Okay. So under different definition, your result will be different. So the first homework we require you make sure you understand what's the for neighboring, egg neighboring, and neighboring, friend adjacency definition, and write out this MATLAB program, and then you can input the same subject, you'll get different results. So your neighboring definition. Okay. For is very easy. Vertical, horizontal, for neighboring. Egg, including the diagonal neighboring. But N is only defined for including the 4 neighboring and also the egg neighboring, but they have to make sure their intersection with your neighboring pixel, their 4 neighboring is empty. So go back to the definition to understand. I'm talking about this now. And the next one is closing path. Okay, so the last one here for this picture we are asking. Oh, okay. Okay, yeah. Right. So now we are talking about this image. The inner boundary of the one value region doesn't form a cross path. Yeah, remember the cross path? Our starting point, ending point will go back together. So this is only the starting point and ending point are not overlapped. So this is not there's no cross path here. So yeah, so it is how the boundary does. For the zero background, yes, they can circle it. Starting point and the ending point will be the same pixel. So this one, please, we have this homework for this connect component definition, and you have to try to write up your own program and go through the test. Okay, if you have a question, come here after the class or come to our office hours. So connect component we define because you are going to extract the subject from your document. Especially for the later chapter, we have the binary operation. So the subject will be the first target from your image, and you are going to do some manipulation and image processing. So you have to define the connect component first, okay? So and then after you define, you can labeling all the connect component, all the labeling. Labeling is just give a number for each subject. So every subject there will be different size, shape under your 4 neighboring, and neighboring definition. Okay, so please go back to check. And also we are calculate the distance for different subject. So how to calculate? We have introduced 3 different ones, Euclidean, city block, and chessboard. So I just mentioned because it's very difficult to give the test to let you do image processing and then compare results. So the easier one is that way I can give some like this definition, and I can get some digital number back, and easy for me to grade. Okay, so just give you a hint. Okay, so let's go back to today's second slide. Okay, so actually in previous slide we understand your human vision, your vision system, and some sampling process, right? Compilation, and you have to do some different resolution. They have different way to quantize your image variable, and we are going to introduce some very fundamental application. How we will do in the following classes, including some image, how to give different geometric application and operation. So from here, the book give you a lot of introduction label. Maybe you will use in different application in your research field. So come to read quickly, and then apply it to your own research. Okay, so here is some noisy image, and sometimes you have to know what kind of noise you are going to deal with. For this one, this is an example taken from Sombrero Galaxy image, okay, and it's from NASA, okay, and because the characteristic of the noise is like a Gaussian noise in the space. So how you remove the noise? Sometimes, okay, the low-pass filter will give very good result. So it's just give you an example. Result of average for average image, okay, average image for 50, 10, 100, 500, 1,100 from the same image you acquired from your satellite image, and you can see from the previous one is a one-shot image, and then if you just take an average, okay, 10 average, 10 frame average, 50, 100, 50, 500, 1,000, the image getting clearer and clearer because the noise in the space that maybe have some specific zero mean Gaussian distribution. So how you do that one? You just apply some mathematics way. So we say the additional image can be summed up by using this way, because we have this image format, obtained image format like this. Your image always has some additive noise. So you have to understand what's the characteristic, what's the features of your noise, or use eta to describe additive noise. And this is your observed image. So you will see this a lot, this question a lot, the format, because your original image, you don't know. Because when you observe image, it's the GSY, but you don't know what's the F. So you are going to estimate what's the eta, what's the noise, additive noise from your observed equipment, observed environment. And then as long as you know, okay, you can estimate it, you can try, just sum up this image. We use some expect value of this image. You can take the average of this image, and sometimes you will observe very good original image back. So yeah, we will take this G bar image as in mathematical way is depend on how many continuous frame number you are going to add up. So see, it's very simple, straightforward. Just add up all this image with in the same frame, and then divide by k. K is we just mentioned, use 10, 50, 100, 500, and easily. If this is the Gaussian noise with zero mean, the noise will disappear. The noise will just disappear immediately. So you can see the image getting clearer and clearer. So yeah, so this is quite simple. And sometimes you add up more, your variance getting smaller, and then you can get your original back. But sometimes some different environment will get different result. So in this case, we say when k increase and our variance decrease is very obvious from this satellite image. How about this one? How about this one? This is the infrared image of the Washington, D.C. And the image resulting from setting to 0 to the least significant bit of the every pixel in A. So what does that mean? So we assume this every pixel has 8 bits to represent the gray level. So we have 256 different gray levels for each pixel. Now, this application suggests to setting to 0 for the least significant bit. What's the least significant bit? So every pixel have 8 bits, right? So this one we say most significant bit. This one is the least significant bit. 8 bits. Every pixel you have 8 bits to represent its pixel value from 0 to 255. So when you have 8-bit representation, we set this to 0. This is a succession to the least significant bit to 0. What do you mean? Actually, this is kind of noise at the end of this image. So when your camera going to capture the scenery into the computer system, if you know the camera system, you know it's semiconductor. So the electronic block flying away there. So add up a little bit, lower down a little bit, their value will be changed. So how they change? At a fixed significant bit. 1010 fluctuation a lot. So we set it to 0. How do you do that? We just remove the small variation pixel value there. And then take the difference of the two images. Take the difference of the two images. So you are going to see what's the noise. What's the noise? So the left one is the original image you captured from your camera, satellite camera. The second one is you modify the least significant bit to 0. I don't care if you are 1 or 2. I just change it to 0. Can you tell me the difference between these two images? Impossible. If you can tell the difference, you are Superman. But for the general person, visual system, there's no difference at all. I will tell you a lot of difference. So you just subtract this one by this one. Just subtract. So let's look at the final bit, significant bit, this significant bit of this image, the variation. And then how can we do this one? This is doing some scale to the range to 0 to 55. So when it's 0, put 0. When it's 1, put 255 to make your visual system can easily tell the differences. Okay, from their difference. So this is the result. The difference of these two images. The final bit. So just give you some idea. The various, the smallest, you think about this is make no differences. But indeed, they have some difference, and you can enlarge their difference and visualize. So it's just enhancing the differences. So if you research, you need to enhance the detail of two different images, of what's your improvement of this your research work. Maybe we can do this way. Try to make deeper impression from the reviewer, and see I have improved a lot. But if you want to restore, don't show it because there's a lot of differences. Okay, depending on your application, right? You won't say I changed a lot, show it. But for the image restoration, you try to correct your image to go back to original. And you compare your result with the original one, still have a lot of difference. You are stupid. So don't do it, hide it. Okay, so for different application, just do some small scale. You can see a lot of difference. So this is difference between the 930 dpi, 72 dpi image in figure 2.23. What's that? It's a watch. So remember the watch? Between this one, so this is the previous image. So you just go back to check our previous slides, and they still have a lot of differences. So for different resolution, differences you can see a lot. Okay, so it's just use some difference to introduce your differentiation, enhance, exaggerate. I can say exaggerate your difference from your operation. So now let's look at the real medical image application. Use difference. So how they get this image? And this we call mesh image. So what's the mesh image? Mesh image is before you evaluate the status of the patient, you just take the X-ray first. I think it's X-ray. Yeah. So you take the first from the radiation, and then get it from your septic field, and then we call it mesh, the first original image. And then the second one is called live represent your blood vessel. And then this is the new one, live one. And then continue, you just take the difference. C is the difference between this one in this mesh image. You'll get this result. So it's a lot of applications using this way. Okay, first one, you take the original static image. And then the second one, do some real-time operation on your object. And you'll see the contour, your target vessel, different conditions. So after you injected the medium to your vessel, and then with the same posture, you cannot move, okay? Same posture. And then take the live image to a mesh the first time, that mesh image, get this difference. Difference is still not clear, so what do? Just enhance the difference image. Okay, through later on we are going to introduce some contrast enhancement. You'll see the result like this. So you can see the medium injected to the vessel, everything is very clear. The vessel and then clear. Very straightforward, not difficult at all. Okay, this is the true medical application used in your real life. Okay, so we call it intensified TV camera image mask. This is intensified TV camera, the first static image, and this is inject some iodine 碘哈，用碘的那种 medium a kind of chemical component, and then we call it contrast medium. Okay, enhance the difference, and then take the difference. So it's a live image here, and then take this mask image here, and then you get the difference, and then sharpening. So everything becomes very clear. And you can see, is there any wrong in the vessel, in your brain? Okay. So what did I do? I just use some subtraction operation, and then I get a very good result. Okay. How about this one? How about this one? Some of you will have the image when you obtain like left image. We call this is a G of SY observed image, right? Sometimes you get this shaded image on certain corner, right? Easily, right? Also maybe illumination, the lighting environment. How can you solve this image? Back to this one. Remove all this shaded effect. How you do that? How you remove the component of this one back to this original. It's supposed to be. Don't be affected by your environment. So maybe a lot of research you have to overcome this problem first, right? Because you want the original clear image. But unfortunately, your lighting condition, direction, always give you like this shaded in the left corner, right hand corner, left hand side corner, right? How do you do that? So the first purpose is find this one, right? If you know this shaded image, can you do that? If you got this one, you can just remove it, divide it. This one, take away immediately. Actually, this is we call the final original image is here, f of xy. This is the h of xy mask image. We call it shaded pattern. Okay, this is shaded. So, if you understand the imaging system, you will see our G of xy actually is obtained from original image multiplied by fhxy. That's the way. So image multiplied by this shading effect will result in this one. So this one multiply this one, get this one. You agree? What's your original image, clear image? Go through your shading system, your acquisition system. That's the final result. That's it, right? Okay. if I can find the h of xy, this one, and I observe this g of xy, easily, just take your observed image, divide it by h of xy, done. Go back to your original, right? Mathematically very easy. But how you get this one? How you get this shaded pattern of this system? Very easy, very straightforward. How you do that? Between exact the same, you can do nothing. The only you can do is bring one piece of white paper. White paper. What? Why? Okay. You look very okay. Yeah. If this is one mathematically, this is one image. What's the result? What's the result? This all one inside this image. Multiply this image. What's that? The answer is just multiply one. Every number, every grade level, multiply one equal to itself. So only you have to keep this environment. Grab a piece of white paper in front of your acquisition system. You'll get H as G, right? Because every one identity multiply this one equal to H. Your observed image, your environment, exactly the same environment. If you define our input is O intensity, or use one say 255, fine. 255, 255, everything is the height, the constant height is fine. And you can estimate, roughly estimate your H of xy. It's very important here for you to do something to correct your system. I don't have to change the parameters of your environment. Keep the same way. The same lighting environment. Just put in constant image in front of your system. See what's the result? Actually, it's just a filter, right? And then if you got this one, you have this H. So every time you got a new G image, G1 image, can you find F1? Definitely, because F1 equal to G1 you observe, divide by H. Okay? Very easy? Because you know the shaded function of your system. Okay? So, next time, if you have this kind of problem, this kind of issue, very straightforward. The problem is, did you notice that I write down dot divided? Okay? The key point here. Anyone know about this one? What's the dot represents? If you know, please raise your hand. Oh my goodness. No one knows? You know my oh, thank you. It's a method issue. It's not a image processing issue. Method issue. Because you are going to use method to write up your homework. So the method is what's the MAT represent for? Matrix operation, right? Matrix operation laboratory tool. Matrix operation for the multiplication. Can you tell me what's the result of this one? Because I just talked to a TA, he is not going to give you the tutorial there, but give you the video there. And you are going to use this a lot. So I just try to remind you. If we have a multiplication, what's the matrix operation for? What's the operation for is multiply these two images. You have to calculate A11 times B11 plus A12 times B21 as your first element, right? So this is A11 B11 plus A12 B21. This is the first element, and this one is A11 B12 A12 B22 plus this one, and this is A21 B11 plus A22 B21, and this is A21 B12 plus A22 B22. Should be this way, right? Let's make matrix 2 by 2 matrix multiply 2 by 2 matrix will get this result. This is correct. You have to remember this is the right one for matrix multiplication operation. But in our image processing, sometimes we need elementary element operation. Our multiplication is hold the same location pixel multiply the same location element only. Don't do this mathematical way. Okay? For example, like I'm talking about this one. This one divided by this one only divide the same coordinate pixel. Only and multiply also. If I'm going to type this one, multiply this one image to get this one, how do you do? Please do not apply mathematical matrix multiplication process. Don't do that. Row-wise, column-wise. Multiply individually sum of row-wise, column-wise. Right? The right matrix operation. But in MATLAB, provide a very easy way to do that right. Only you have to do is put a dot in front of your multiplication operator. So if you change this one to dot multiplication, in front of multiplication, add up one dot there. We call it dot operation in MATLAB. What's the result? It becomes elementary operation. This one times this one, we'll put here. This one times this one, put here. This one times this one, here. This one times this one, here. Only element-wise operation. Okay? Very important. We call dot operator. Dot operator in MATLAB. Like division, dot, divided. So only three different. And three operations in MATLAB provide dot operator. Dot multiplication, dot division, dot exponentiation. Okay. So the third one will be this one. So you have dot multiplication, dot division, dot power, the power of 2. Okay, power of 3, power of 5. If you use this one, we know it's dot exponentiation. Okay, every pixel will be processed element-wise. We are not going to follow the traditional image processing tool. Is that okay? I hope you just forget to raise your hand. You know it. Okay, MATLAB is very powerful tool for you to do some matrix operation, but they provide this for image processing. Dot, we call it dot operator. Dot operator. So you have a 3 dot operator there for a matrix application. Okay, they do it element-wise. Depend on location only, depend on coordinate only. They don't do this traditional way to do some multiplication. Okay. I hope you agree. But if you don't agree, you cannot use MATLAB. Okay, so we have this one for this shaded multiplication and division for the shading correction. So we call this shading correction. So sometimes in your application, you observe your image like this one. Sorry, do some preliminary processing for your image. Go back to look at this original one. They get a very good one. So divide it, dot divide it, pixel by pixel. And I already tell you how to get this environmental shading pattern, how to do it. Okay. How about this one? This is the masking operation. Masking operation, masking style. So sometimes we are doing some application. We are not going to do whole image, only partial of the image, sub-image. So we need to define some mask. Mask operation. So how will we define the mask operation? First of all, you have to know this keyword. We call it ROI. So you have to define your region of interest. Okay, so you read a lot of paper, you will see this keyword. Region of interest. Okay, and we are going to see, okay, I'm going to find some sub-image I'm going to process. So define region of interest, and you just can do some operation, and you can see the result of the image, like the right-hand side, this one. So when they operate visual image, and then product of A and B, A, B, and then this is dot multiplication of these two images, get this C image, right? So don't do traditional matrix operation, only do element-wise multiplication here. So get this result. But most of the time, we are not going to use this image directly. We will do some transformation for this intensity. How we do that one? So the traditional rule is we hope our process image always located within the pixel value. Your sub-image should be belong to 0 to 255. And then do some different operation, different filter. So when you get this sub-image, this is not from the whole image. So how do you do that one? So scaling this image, this small image, to this range. That's a traditional way. Try to rescale your image to a standard range. So how you do that one? So it's quite easy. Okay. So you just find the minimum value. Okay. So you get this GM image. Actually, all write in textbook. So how you do that one? So you find out the minimum of the G image, and then you minus, take away. So if you want to create image with a minima to 0, so you divide it by 0, divide the small one, everything will track down 0 as the minima point, right? And then scale up. So the first one is minimize. The second step is scale up, scale the image. So how you do that one? So if we want the image belong to 0 to K label, K is 255 if you add bit image. So you have to do is scale image. The final image will become what? Your minimize image, remove, and then divide by max of GM. It should be not simple. Okay, imagine this image is take away the minimum value of the GX. So everything becomes, the lowest value becomes 0, right? Because you take the minimum number in your sub-image, take away. So the image becomes 0 with the lowest value in your image. But everything goes down. So how you scale up this to 255? Very easy. You just find the GM. And then your number, your pixel value, intensity value, divided by this 100 multiplied times your purpose, maybe 255, maybe 127. Directly, you transform your image to this range. Scale image to 0 to K. K could be 127, could be any value you are going to assign. So stretch up, scale up your image to certain range you are going to process. Okay? Kind of enhancement we will see immediately. Any question? It's very standard process for your extracted sub-image from certain part of your original image, because you are going to transform all the gray label into defined. Traditional one is a 0 to 255. But okay, maybe you after this some subtraction, the value only between 0 and 100. So you are going to scale up. So we call it a scale image. Actually, it's called clipping process plus scaling process. Okay, try to change your image to the standard input gray label. Okay. So think about what's the application. Actually, all these process we will use a lot in the following chapter, but we will not mention again. You have to remember this fundamental skill. And in addition to this gray label image, actually sometimes you have to process some binary image and a lot of set operation. So the chapter 2 also introduced some important set operation in your image and their relationship. I think it's very straightforward. So just take a look quickly. You know all the set operation, some intersection, some union, some commutative rows, some associative rows, distributive rows, De Morgan rows. Okay, so it's some kind of straightforward for set operation. So if you don't understand, try to use a Venn diagram to see, and you will know intersection is like this one, intersection and union, and what's the E? E and the G are the same. What's the E and G are the same? E and G. Oh, yeah. Okay. So A minus B set. You can see your A is the circle, and minus B is the only shaded area left. And this is the A intersect with B complementary. So B is here. B complementary is outside. And A intersect with this B complementary, so equal to A minus B. So definitely their result will be the same. I think it's very straightforward for a set operation. So we'll skip this one. How you apply that set operation? Actually, set operation is very straightforward for the binary image, right? Imagine that because your image only has a 0 and 1, gray or white. So set operation very straightforward. Just do some intersection, union operation, immediately get a result. Complementary, easy, 0 to 1. 1 change to 0 because complementary. Okay. So very easy for binary image. However, in the later chapter, 9 of morphology operation, we are not going to deal with binary image only. We have to deal with gray label image for the set operation. Right? Okay, so set operation not only used in binary image, also for the gray label image. So sometimes you are confused. But we are going to look at this one quickly. Okay, so our representation for the image, we call it set operation involving with grayscale image. Set operation. That's very easy. You for your background, I think you only know binary 1 0 1 0 to see that the Venn diagram, right? The Venn diagram very easy. Just tell me, and I can see what's the result for this set operation. But we are doing with set operation involving gray label image. For image is gray label. It's not 0 and 1. So how you do that? It's some number there, right? It's not 0 and 1. But definitely you can change your gray label to binary image first and then do the set operation. But now we are going to do some morphological operator, but let's use a set operation. But you have to define first. We define C of X, Y, Z. Original, our image is X, Y for location, coordinate, X direction, Y direction. But now we add one more, Z. Z dimension is for gray label. Okay, so this spatial coordinate. This xy is also coordinate, but this is the intensity level. So every pixel we have a coordinate. We also have the value, and we are going to define what xy. So if this is image A, so what's the complementary of the A image? What's that? So in your previous impression, you know it's 0, 1 change. But now we are going to change like this one. It's become, what's that? It's become S, Y, and the third value is K minus Z. We use right the same character. And S, Y, Z belong to A image. So now this operation become what? Your K is your maximum intensity level in your image. If you are doing 8-bit gray level image, this becomes 255. Similar to 0, 1, but now it's not 1. It becomes 255. So it's changed to this way. So complementary of this one, if your K equal to 255, then it's use 255 to minus. So how about union of two images, two grayscale images? I'm going to do union. So complementary, we already know, it's just a negative of your original image, like your negative film, okay? But now it's a union. We are going to know union. Union, if your operation, you know, finally, you just draw the Venn diagram, you know the result. But now it's become max of this Z and A, B. For A belong to A image, B pixel belong to B image. Okay, so it's not yes or no. It becomes, you are going to take the maximum value of these two pixels, the max operation, set operation for gray label image. So later on, in the morphological chapter, the set operation for the grayscale image is not 1 or 0. Okay, you are doing the Venn diagram, only have the location. But now everything will become some value there, and we are taking the maximum value of that one. Yeah, so let's look at this example for this for the class ending this hour. A is the original image, so easily, right? You take this X-ray scan image. I don't know, it's a maybe positive image from the G medical system. And B is a negative. Negative, we just define the negative of this image. So it's become 255 minus your original value. And C is the union image of A and the constant image. So see, that image is original one. This one is not this add together. This is add up some specific. Actually, I remember it's some average value of the previous image. Okay. Some average value. How many balls? Let me check. It describe. Just say a constant image. So the next one image is the A image. Add up some certain constant label image. I remember it's some average of the A. So you take the average value as a constant, maybe times 1, times 2, times, and add up together, you'll get this kind of image. Try to enhance brighter image. What you want to look at. It's different parameter will give you different results. So very easy additive subtraction operation, multiplication operation, and you can do a lot of different purpose, and you can look at different locations you want to look at. Negative, blah blah blah. So it just tell us this is the union of the image of A and the constant image. So now you know set operation union is different from what you know in previous binary image. Let's do some comparison, and then make the maximum value instead of some grade level. Okay, so let's take 10 minutes off, and we'll come back to continue. 这样就好了。Okay, yeah, we have some signatures document. Please come if you didn't sign yet. 我签呢？对，好啊好啊。回干嘛？哦，你去拿，没关系啊，不急不急不急。 谢谢。继续。哎，哦，你已经按了这个，那我再继续。对。
就按这个就可以。
OK， 好。Okay, so there are some logical operator. Okay, you know logical operation is just 1-0 operation. So you just consider foreground is 1 value. Okay, pixel is 1 is foreground, and background is 0. So you can doing some binary processing for this operation definition. And this is kind of illustration of this logical operator. I think it's very straightforward. It's no challenge at all. Okay, white and black. So for binary image. So like this I think we can move that. So sometimes in the grayscale image, how you this one? So it's a spatial. We call it a spatial operator. Okay. So we change to this spatial operator. It's an intense transformation operation. Actually, for the spatial operation, we have two main domains. One is located in spatial domain. The other one is will be frequency domain. For the spatial operation, we have three basic types. The first one is a single pixel operation. Okay, for the spatial. So we have three different types. First one is a single pixel operation. The second is neighborhood operation. The third one is geometrical spatial. Okay, basically we have three different types. So step by step to do that one in chapter 3, chapter 4. Okay. The first is single pixel. Single pixel. So how do you do? You are going to modify your image to a better version, better looking, whatever. So the only thing you have to do is find out the transformation function. Transform single pixel gray label to the other gray label. So actually, you are going to do some lookup table transformation. Okay, so we call this first step is just like this equation, S equal to T of Z. Find this transformation. So alter the intensity label at each pixel individually, and using this transformation function T. So you from a specific gray label change to the other label. So the application is trying to find a T. How you define this transformation function? And we always have this kind of here, this kind of plot. So what is this plot? You see the plot. This is the original gray label, 0 to 255. And you are going to define a T transformation, T of Z, change to 0 to 255. And what kind of function you are going to define? So in chapter 3, we'll see a lot different transformation. And this one is very simple example is a negative transformation. Just say, if you see this one, if this blue color for this one, T of T equal to this, it's a linear. And when your original is 0, it changes to 255. For your variable original, if this point is 20, and maybe 180, change to 175, minus 180, right? Whatever. It's just a negative process. So this is one of the example. Get right hand side result. So it's a negative operation. Easily get this one from left hand side image. So it's called pixel, single pixel operation. And we have different one. Second one is the neighborhood operation. So this is example for the neighborhood operation. How we define this one? So you have to find out some operation like this. So, for example, this one, heart vessel. Okay, from left hand to right hand. So you doing some smoothing effect. Smoothing effect. How you do that one? You have to find out your mask first, and then transfer every pixel to, like this one, is a low pass. So you are going to find out RS in this sub-image, sub-mask, and then F of R, RC, oh, you RC here, RC, the same. So what do we do this one? So we see we have a sub-image, the original image located at XY, and we have sub-image XY with the mask size n by n. So we are going to change to a new variable, intensity variable, but that is XY, the same location. And we try to use a mask neighborhood relationship to modify it. Different from previous single pixel transformation. So we use neighborhood information. So we have to define how you do it. So in this example, we just sum up your neighborhood intensity value. Sum together, divide by how many pixels you sum up. So see n by n. So original pixel. And then define the sub-image XY, and then know your m and the n size in your neighboring. And then sum up together, divide by the number, total pixel number, n by n, and then every pixel value will get this result. So every pixel is from here, the same location, take their neighboring foot, sum up together, divide by the total number of pixels. You get a new great intensity level for there. So we call this neighborhood operation, one of the example. We'll do a lot in chapter 3. Okay, the third one is geometric spatial transformation. So very popular one is affine transformation. Okay, so it's a geometric. You are not only to change the value of the pixel, but also the location of the location of the pixel. How you modify? It's called geometric transformation. We also say this is a rubber sheet transformation. So this is a geometric. Sometimes you will see they mention this transformation is called rubber sheet transformation. So what does that mean? Rubber sheet, 橡皮. Oh, yeah. So it's just printing your image in a rubber sheet, in a plastic rubber sheet, and then you stretch your rubber sheet, your image will change to different shape. Okay. So this is geometric transformation, also called rubber sheet transformation. So you just shrinking your image compared to original one. So there are so many different operators. Famous one like the identity, scaling, reflection, location, translation, shear, vertical in vertical way, shear in horizontal way. So you can see this is their result. It's a kind of simplified. So you just define the different coefficient here. So like this one is just identity E111. So it will be translated to the same location, and the grade level is also the same. So in this sense, we have the identity image there. How about if I define the new location will be the original coordinate, like this one. So what is this kind of geometrical transformation? I define this function is just easily 20 by 2 for every original coordinate. What's the result? Actually, it's just kind of shrinking. So every 2 points become 1 point. Every 2 points become 1 point. So your size will become small as its original 1/4. Okay. Every location coordinate will jump to 1/2. So it's kind of shrink to original image to have in horizontal direction and the vertical direction. So it becomes 1/4 of the original one. So for this geometric transformation, actually we say it's there should be two basic operations. The first one is spatial. Just I mentioned this example, spatial transformation of coordinate. Okay, first of all, you have to decide. You have to decide where is the new location you are going to transform. So geometry you have to define. So the first, these all the position you are going to change their location. And the second step is the intensity label. How you change this pixel to a destination location, and how you put the number there. What you put the intensity label there. So the second step will be intensity interpolation. Let assign to the new transform pixels. So it's very clear. So I'm going to change the location of the pixel first. I have to decide it. And then what's the intensity value I'm going to put there? So sometimes it becomes larger, becomes smaller, and I have to decide it, how we do it. Actually, we have described this before for this assign transformation and for intensity label assignment. So for the spatial should be no problem, right? So you just assign how many positions you are going to do it. How many like this sure change to there. This located the same, but this is rotated of the image different degree. Okay. If you turn it counterclockwise, the theta will be positive. If you try to turn clockwise, the theta will be negative. So as long as you already decided where is the new coordinate you are going to put, the second one is the intensity label assignment. So intensity label assignment, what do you do? It's also 3 ways to do that. So you can just assign the nearest label, pixel neighbor, and then just put it there. Or you can do some, in that case, I mentioned bilinear or bicubic transformation. Depend on your 4 neighboring or 16 neighboring to decide it. Okay, so here is some example. This is the image rotated minus 21 degrees. Okay, so how you do this one? This one we just mentioned like this. Okay, and then transformation there, and we are going to this is the angle is 21 minus 21 because the clockwise. And then if you this one is the original. If you look at this point here, I don't know if you can see this one here with a rectangle annotate, right? And then put here. Original one is binary, 255 for the white, 0 for the black, right? And then you rotate. The first one is V image is rotate using nearest neighbor. So we say there are 3 different ways. Traditional way, there should be a lot of different solutions, but the most common is use nearest neighbor. So see, this one is the nearest neighbor. We mentioned nearest neighbor. So depend on if we open this small box here, see, there are some stair effect, right? Not good one, but it's very easy. You just approach by nearest neighbor. See if it is 0 or 5, 255. So you can see the value only 0 or 255, 0 or 255 as a result. So it's look at the pixel is 0, 0, 255, 255. Just look at the neighbor of your original one. And the second one is bilinear. Bilinear. So your V of new position will be what? Will be A x prime plus B y prime plus C x prime y prime plus D. This is bilinear transformation. So you just look at 4. Sorry. So look at these 4 points. 1, 2, 3, 4. Put a 4 point there. Okay, and then try to solve the coefficient. And you see how it's changed. Where's the location, and look at their neighboring. 4 neighboring pixel. 4 neighboring pixel to solve this the coefficient. And then you will see like this example. If you use this bilinear transformation, it will become what? Become like this way. So this is not 0. This is not a 255 anymore. It becomes your neighboring. 4 neighboring. The value will be changed. Okay. So it looks like better than this one. This one is stairwise. 0 to bit, 0 to bit. But there are some variable there. So looks smoother. Okay. The next one is the bicubic. The traditional one is I think it should be bicubic. D is bicubic. Bicubic, you just look at more neighboring pixel, 16. So they will have like this one is G, I, say the coefficient will be 16 from E to 0 to 3, 0 to 3. So you look at 16 neighbor. Okay. And this is X, I, Y, Z. So you'll see how you solve this 16 coefficient from your original neighboring, 16 neighboring, and then transform to here. So the value will be decided by your neighboring. Depends on your neighboring pixel, and then get the result by cubic and by linear. Okay, so actually later on we don't process this more, but just give you some hint. Maybe your research need to do this one. You can do this first. So it's all put in chapter 2. At the first glance, for you learning this digital image processing, you can choose how to how to choose the following chapters. Okay, sometimes your rubber sheet transformation, you will face this kind of problem. Okay, so because you are going to rotate, and once you rotate, the size will be different from your original one. So as you know it in advance, you have to enlarge your destination image first. Otherwise, you will get some weird operation there. So give your image template larger to solve to satisfy all different location, angle, and then get a good performance. Okay, like this one. This is the next application we call image registration. Okay, so what's the image registration? In Chinese, we say the 影像校对. Okay, so if you have some different transformation, you are going to recover it. You are going to do some image registration to inverse its image to the original one, but you have to measure what the differences. So we do some correction, and so we call it the image registration. So you have to need one reference image first. And our transformation, maybe there are several ways. Okay, in research we have a feature-based or intensity level-based approach. Here, just give you some very easy example. We are going to align 2 images together and see what's the difference. So this image definitely be transformed, geometric transform to different shape. And you are going to recover it, do some image registration, try to correct what's the difference after your anti-transformation. So see, we look at this point here. We are going to transfer back to the original one. So you can do some inverse geometrical transformation, and then they will become like this one. So this one is a get from this one, and you are going to do some correction. So you do some comparison, and this is the result of this application. Difference between the A and the C show more registration error. So we say this is the registration error. You do some image registration, but unfortunately, after your process, there are still a lot of difference. So we call it image registration. So after geometrically distorted image, we are going to inverse and then This is the register image, and then compare the difference, or get some result. Is that okay? We are here write some more detail for the spatial geometric transformation. Yeah, if you are interested, we can put it in. Should I do what's the time? 34. Okay, some of your research maybe really need to do some this geometric transformation. Let's see. Okay, we just say we need to transform from this one to maybe different location here, and you transform to a exactly location, and you are going to write down what's the grade level you are going to put. So sometimes you need this. We say you need I don't know. Did I give this example in this time? Give you four point grade level. This is 10. Did I do that in this week already? Okay. So yeah. So go back to check that one. Okay. So this is the location you are going to find the new value. So you have to define the coefficient first, and then after that, every pixel you can do that. You can find out the new location, right? And after the new location, you are going to define the intensity level. So the zero order, we say it's a nearest neighbor. So just put in the nearest neighbor, and the bilinear interpolation is for nearest neighbor, and the bicubic 16 for this is bilinear, and the bicubic is for 16 neighboring. So I think it should be just like I mentioned the coefficient here, ij, yj, and then summation from 0 to 3, and you will see 16 level to 16 coefficient to solve. Okay, so we say that one. So okay, just please go back to check our previous slide. The chapter 6, we're talking about the color image. So from grayscale, from binary to grayscale, and then we are talk about the color image. Actually, color image is composed by 3 different sub-image. Okay, in red channel, green channel, and blue channel. So actually, every pixel here is formulated by 3 different pixels at a time. So it's called vector. Vector formed from this corresponding position pixels value in 3 sub-image. So it's red, green, and blue image here. And we are going to do some general approach. You can do it in separately and combine. Also, you can combine together and to solve it. So in chapter 6, we'll do that color image transformation. And here is approachable in a linear transforming domain. So here, just try to summarize. In spatial domain, we are going to do some transformation from fx and do some operator here, and then or sometimes we change it to frequency domain. Okay, transform domain. So different domain you can choose. Okay, here we use spatial. We just introduce a lot of different approach. Now, if it's not enough, you can transform it into different domain. The most popular is a Fourier transform. And how you do it is always the same. The t is equal to some summation of f x y times r x y u v. Trying to use this transformation kernel, and x from 0 to n minus 1, y 0 to n minus 1. So it's a standard transformation operator. So this is the transformation. But for the Fourier, we are going to define the r equal to what? The r. If you use this minus j to pi ux plus n vy. So you see, we are going to change this function to frequency domain. Here is the Fourier transform. Yeah, in your MATLAB, actually, just remember one keyword for 2 dimensions, just this one, and put your image here, and you will get it there. UV here. So actually, they do some transformation like this way. And this kernel defined as this function. So it's a Fourier transform. And you will transform your spatial domain into briefing domain. Why we do that? Because it's much easier to you to recognize your requirements. For example, like this one. The left-hand side is the image you acquired from your computer. Okay, the left-hand side. This is spaceman on Earth, on Moon or not, I don't know. The NASA image. Okay, so you'll see a spaceman here. Once you get this kind of image in front of you, how you do that? How you do that? If you have done this image processing, immediately you know there's some noise there. And the noise is great, very easy to solve. Why? Yeah, you have image like this one. There's some curtain back in front of you. And your original image is noise graded by this kind of specific pattern. Okay, remember, as long as your noise is frequently appear, you can view it in briefing domain. Very important conception. Frequently appear. I just don't know what's the frequency, right? So as long as you have to do what? Transformation, Fourier transformation. Transform from spatial domain to briefing domain. So when I see this repetitively noise transform to image domain, you will find out they have some conjugate point there, the energy. So the result will be like this. More significant, more obvious frequent pattern. Here the energy is stronger, especially dot point, dot energy there. So if you remove this two dots from your briefing domain, that all is background energy. Actually, there's some energy here, high frequency. Here's the center. Center is the low frequency part. Okay, our image, our signal, every signal have their different energy distribution in briefing domain. And the DC value is a frequency equal to 0, and some low frequency band, high frequency band. So for different band distribution from 0 to high frequency, and you just transform to Fourier domain, briefing domain, you'll see every energy component. For this image, I even don't have to look at the brief. I can expect there should be two dots. Why two dots? If you know the signal processing, Fourier transform is a conjugate pair. Conjugate must be okay. If you come out with only one dot, something wrong. You didn't see the whole view. And if you don't do shifting, okay, actually your transformation should be like this. Dot here and dot here. The other dot should be here. So actually you have to do some shifting process. This is a 0 frequency at the original. 0 hertz, DC value here. But you have to do some frequency shifting. Shifting the low frequency into the center part, make it easier to observe. So this is the after shifting from upper left-hand side corner to the center. So the lower frequency, 0 hertz, DC value will move into the center. And here is some repeated. What's a repeated? There's some sinusoid form there. So you see this pattern? See? Right up, so there's much some frequency here. So the frequency is a sine, cosine. Sine, cosine transformation in briefing domain become an impulse spike. Impulse spike image is a dot point, shining dot point. So if I look at this two-dimensional, I know there must be some impulse noise created for this image in briefing domain. So undoubtedly, the transformation result just like this. Just like this. The frequency component will be very clear spot in conjugate location. Okay? So once I get this image, very easy. I just remove the dot point In frequent domain, remove it. Okay, change it to 0, and then inverse back your spatial domain. The result like this. Immediately, very easy, straightforward. So, that's straightforward. As long as you know what is the Fourier transform, what's the frequent domain represented for image, very easy. But we are going to process not so easy image. Okay, so this is kind of image restoration. Remove some additive noise in your image from this one to this one. Okay, so this will be taught in chapter 5 or 6 for the Fourier domain operation. But you know, if you don't know the Fourier transform, the background theory, but you have to know these 4 characters. Okay. Yeah, and the inverse is IFFT2, the inverse transform. After you process it, you are not going to give me this image without the 2 impulse function. Okay, I need this one. So it's only 2 is IFFT2 inverse Fourier transform. You'll get a result. So the following is some events of this explain conditional probability. Okay, so the next one will see some probability issue for image processing. Very important because we are going to do some pixel operation. And how to do pixel operation we mentioned, just change one gray label to the other gray label, right? So the first step is try to understand what's the distribution of your image. So for here give some image here, right? This is a mimic simulated image. And if you look at the distribution of the image gray label, it's only 4 different colors, right? And every color has their pixel amount, pixel number there. So we call this is a histogram gray label of this image. So there are only 4 colors, so there should be 4 spikes. And the sum up together will be the total number of this image. And if you divide this number by the total number of every impulse, every spike represents the probability of the gray label within this image. That's it. So it's a probability issue now. So every gray label distribution we can see from this histogram distribution, corresponding histogram. So this one histogram and this one real image, the histogram like this one. So there are 256 gray label, intensity label in this image, and you are going to look at counting. So just write one. There's some distribution for white one. The black one is a more black color here, so it's distributed located in a low level. Here's a dark, here's a bright. Okay. So our next chapter will start from here. So we are going to understand what's the distribution level of your intensity distribution level of your image. How you do it? How you enhance it from this one? How you process your image from this one? Because we are going to do pixel transformation. Okay, so that's a histogram of the image histogram. Okay, and from histogram, if you don't see this one, you just see a histogram of image. You don't know the content, but you know the trend of the gray label, right? If I just look at this four spike image, immediately I will tell you there should be only very simplified image, but I don't know what's the shape of the image. And I look at this histogram, I know it's a dark oriented image, and only part of bright subject. Okay, so but I don't know what's the content. So there is some distribution of the histogram. Okay, so this is from here you can see it's located in a specific location, and this is the distribution of the image with symmetry or non-symmetry. So this one skewed to left, so it's become darker image, and this is normal distribution of the image.
it's fine. You just look at a histogram, and there's an example for this chest image, and you will see from this different grade image, you have different effect, different histogram. So this one is brighter, so located in the right-hand side of histogram. This is the median, located in the median. This is dark, so the dark side it will have larger component there. Okay, so we are going to do some histogram manipulation. How to change it? So I just mentioned important one, like this one, is squeeze to the right sharp in right-hand side. So it must be unclear, but very bright. So if you look at this one, easy to enhance this image through histogram correlation. The only thing you have to do is stretch out. Stretch out this distribution. Every pixel change to here with the same shape, and the image will become very clear. We are going to enhance the contrast of the image without changing their relationship, but only intensity level change one by one. The lookup table, okay, maybe this is 128. So I change the new image 128 to 0, 129 change to 3, blah blah blah, and check out the best location for this intensity level transformation. So you will see the contrast will be enhanced immediately. So we are going to do this histogram manipulation first. And histogram distribution we just mentioned is just like a probability density function. So add up all the spike, the portion of the spike add up is 1, just like a probability. So every histogram you can describe it's just like a what? Like a distribution of the probability, and add up the area here, add up should be 1. Because all pixel there. And we will use a cumulative density function as well. Cumulative in probability, you know, is just add up. When the first one plus this, the second one by one, until it's become 1 there. So if original distributed only in A to B label, and for the component corresponding cumulative density function will be like this one, because it is a square, so it's become linear cumulative transfer function. And this is some Gaussian. Okay, Gaussian is important in our application, image, especially for image processing, because in time domain, spatial domain, Gaussian shape change to Fourier domain is also Gaussian. I just remind you this very important transformation here. Fourier transform is also a Gaussian. And if you have a wider change there, become narrower. Okay, so inverse relationship. So why we say that one? Because Gaussians have this very beautiful characteristics. It's most in spatial domain, time domain, and Fourier domain, all same Gaussian shape, but with different variance. Sigma 1, and this is sigma 2. So your sigma 1 go there is sigma 2 is higher, and and change to here become narrow. Okay, so if this is the frequency domain, you are going to design your filter, low pass filter in wide or narrow band. You are going to design in your spatial domain with different conception. So if you want a narrower, here you must be a wider Gaussian distribution in your mask. Okay, so this is some idea for the PDF. So I'm going to skip this one. This is the probability. Okay, this is all probability. So just let you know the percentage of the sigma definition and their corresponding proportion. Okay, so it's just some real distribution for this Gaussian PDF. Yeah, so chapter 2 will end up here, and we will use all this content in our following chapter. We still have a few minutes. I'm going to start the chapter 3. Okay. Chapter 3. 你没有上传? Oh, okay. You remind me. Can you download now? We still have 5 minutes. So chapter 3 is starting from pixel transformation. 用放在这边直接在上面放。对。Okay, so we just give you some initial idea. So chapter 3 is enhancement, and we have how many enhancement approach we mentioned? Pixel-wise, neighboring-wise, right? So we are going to do both application. 你没有的，我没有放。Sorry. So that's fine. Okay. So I'm sorry because too many things. Okay. We are going to do single transformation, like we mentioned in chapter 2 here. The first is histocoherent equalization. Okay, and how we do that one? I remember all the slides is try to give you how to define the transformation idea first, like this one. So we will come from pixel transformation first. So this is negative, right? And how, if I define like this one, this one, we have a lot of different one, different transformation. So every transformation function will have a shape like this one. Let's mention this one. This is power law. The original gray label here are here. This is the S new label here. So we have a function like here, T of R to S. How do you think the image becomes darker or becomes brighter? Should I use this power law transformation with different power? We define a shape like this way. Your image, this is a pixel transformation, right? I just dealing with the intensity level one by one. This is lookup table. You give me one value here, and I give corresponding value there, right? This is R1, I will have a S1 there. This is R2, I have a S2 there, right? Corresponding value. So you just give me a one lookup table. But if we are now defined like this curve, what do you expect your image to look like? Try to this one into this curve like this. You will see, the darker one will become very bright. Very small range here. Become very large range here, right? Transform. It's a small range from 0 to R1, change to 0 to S1. So everything in dark, original one, located in the original one, 0 to R1, small, very dark one, transfer to the new image, become very bright. Because S1 is much larger, lighter, right? So your image will wash out. So this image, we perform this transformation, become wash out. Very shiny, very white. So it's not good. So what do? You're going to change inverse. Very easy. Choose this one. Okay, choose this one. This shape. So your original small R1 in S1 very small, but extended, right? And try to darken your image. Your bright color here, R2, very bright one. Change to S2 here, still dark, right? So it's more range there. So your range, you can see everything large range become very dark. So you darken your image. So this one, suppose if you try to enhance it, this kind of power will give you better idea. But just change. We didn't change the shape of the image, but we just change the intensity trend. So this is very straightforward. Linear transformation, nonlinear transformation. As long as you can define T of R, like this information, T of R, how to define it? Maybe it's R to power to this one or square. So it depends on you. You like this one or like this one. And I will tell you the result. There's no absolutely good or bad. It depends on your visual system. So your homework, if you're doing image enhancement, there's no standard answer. No standard answer. The answer is like that. Where is the answer? Yeah. You see, he's reading. He says it's good, it's good. He says it's bad, it's bad. So I'm sorry. Discuss with him. Okay, he's grading your homework. So image enhancement, there's no standard operation. Okay, but standard measurement. Okay, only depend on our human vision. It's good, it's bad, it depends. Okay, but in the chapter 6, image restoration, yes, it is, because we are looking at SNR restoration, which means we are going to recover, remove the noise, and we have a standard measurement. We call it signal to noise ratio, SNR. Is it improve it or not? Actually, your operator. So there's no argument. Your paper will be on the one. But if you say, how about my research focus on image enhancement? How do I make the reviewer's favorite? How do I make him to trust my result is good? How you do that? You have to do some survey, sorry. Right. So you look at all these people here and then, okay, please check it out. Is it good, bad, or not? So give a statistic. So if there's 80% people say it's better, okay, just show the result to your reviewer. If it is 80% say it's worse, try to improve yourself more. Okay, so enhancement there's no standard criteria, only depend on human vision subjectively. So you have to say good work to your TA once you have the image enhancement homework. Okay, so let's stop here. If you have a question, please come here.哦，我还没上传呢，你没提醒我。
我刚才一开始问老师说是不是只有一个题？
哦，你跟你讲那件事啊？对对 ，sorry。我一直以为我第3章都已经放了，我已经看过了，上礼拜就放了。
所以讲那个，这作业完成之后跟这个主教，然后
交给他。
这个刚刚说的 enhancement 就是增强部分什么关系？
没有，那怎样？我还没有出那个。
那个 enhancement 那怎样？那是下一次作业。
对啊，下一次，你这次不用讨好他。
所以下一次作业是给他。
就期中考前吧，我大概就4次。
所以是刚刚讲的是下一周。
对，我们这次只有3个 homework， 那个 connect component 已经一开始讲那个，好，3个题目很简单，上面看，放了嘛？
对，已经放了，都放了。
啊 ，sorry， 你也跟我讲白一点，我。
可以帮我贴。
来。
谢谢。那个他需要打勾说要做什么事这样。
OK， 教材，那你就打勾就好了。课程那群组有吗？
没有。
EMI 课程教学。实务操作、作业批改、教材准备，所以 homework 有吗？作业批改有吗？好，来。
直接在里面填，后面这是我的资料，然后这边填。
好，谢谢。
他这个助教我还要去参加他的培训。
哦，对啊，去上个课了，去了解一下。来，那这帮我收。
不晓得。
有人有买，没有人跟你问。
没有人问。
如果只有这个给我就好。对，这我的东西嘛。
对。还有传输线2个。
给我就麻烦在那就好。
好。
不用充电。
哦，我忘记。